So here's the third feature, fast point concatenation. So this is one that uses one of Azure's specific features that's very useful. So one of the steps in cloud clustering is where each worker assigns each point in the partition to the closest centroid. So it's doing that assigning. And the points in the old points blob have to be overridden with the new points that are reassigned. So, but Azure blobs don't support random writes. So the workers can't modify the blob in place. How do we take care of that? One way of solving the problem might be to have each worker write to a separate temporary blob. So the workers just write to new blobs and then send those URLs to the server, and the server can just join those all up in one pass. But that's pretty slow, of course, because the server has to read and write the entire list of points after each iteration. And worse, during this time, the workers are all sitting idle, so we're just wasting large amounts of money. So so it basically takes time linear in the number of points for the server to do that. So a more efficient way is to take advantage of Azure's block blobs. So here, each worker can upload its partition to one or more blocks, and then send that block list to the server. And then the server will join up all those block lists and just commit them all in one big operation that takes just constant time. So this is sort of an unusual use of Azure's feature to get this acceleration, point concatenation. Any questions?
One thing, you've always indicated that the points were in a single blob, and I wondered from the first time you mentioned that, does it make any difference if you have the initial point list distributed over a bunch of blobs in terms of bandwidth, or is it pretty much the same?
I haven't tried having multiple blobs. I think Azure Scope has something to say about this. I'm not sure what the conclusion is.
More blocks, right, guys? Having more blocks would actually increase the
Always
bandwidth.
containers next level. So.
Okay, so finally there's dynamic scalability. So cloud clustering supports adding adding more workers in the middle of a job, and the system will just take care of them and start giving them work after the current iteration is over. So let's see here, how that works is so the worker once it comes alive, it sends a sort of I am alive message to the server, and the server can now start assigning data to it. And so one crucial thing here is that the server has to repartition the points blob to give work to that worker. So that creates some issues with caching, because some of the part of our cache is useful now, part it's not. So currently the solution for that is just to discard the old cache and get a fresh one. But of course, it'd be more efficient to calculate what part of the cache we can reuse, so that's future work. So here's a demo. In the interest of time, since I'm sure you folks have to leave soon, here's just some screenshots. So here's the initial UI, and here's the final result with this point visualization just for 2D points. It's kind of nice to see. And here's these 4 workers that are running, and there's the performance logs that show the time that every task is taken. Oh, and there's
how
also,
long is that, and for how many points?
this is for it's for a small 500,000 points. It was just a demo run. So finally, let's go into the results. So the goal of this project was to gain experience with building data-intensive algorithms on Azure. And the reason for this, of course, is that our team, again, is building this machine learning toolkit on the cloud. So here's how that happened. So first of all, after building cloud clustering, we concluded that Azure is an appropriate level of abstraction for these data-intensive algorithms like k-means. So k-means can be built on all 3 of these systems here, but Azure is in sort of the sweet spot in terms of abstraction. Compared to EC2, for example, it provides easy access to tools like .NET, it provides automatic updates to our Windows servers standard. Compared to MapReduce, it exposes functionality like local storage, multi-core workers that let us get these significant performance optimizations that I described earlier. So Azure sits in this nice area. But it does have some potential areas to be aware of. So
What?
first of all,
Problems?
Cover his ears.
So, well, first of all, as I mentioned, on the cloud, cost scales directly with usage. So, so this is unlike in standard traditional clusters. So we found that, as I mentioned, using multi-core parallelism, we got a speed up as we increased the instance size, but it wasn't linear. And so sublinear is not good enough because we could have just converted scale up to scale out. So then for data intensive algorithms, data affinity gives a good speed up, so 2x for the small size workers. But it does come at the cost of scalability, although we worked around that, and fault tolerance. We haven't worked around that. So scalability is more complicated. We need 1 queue per worker. Fault tolerance is even worse. We need some sort of complicated system, like some sort of buddy system with fault partitions, and I'll go into this in future work. But so that's a difficult problem. And then finally, it's very important in general to do performance testing to figure out those sweet spots for these data intensive algorithms, because so for example, we found that the medium instance size is the best, and similarly, the instance count. I didn't show you this, but actually, I also benchmarked with 32 workers as well as 16. So for scale out, 1, 2, 4, 6, 8, 16, and 32. And 32 is actually slower than 16. So at some point, the overlay.
Fixed size of data?
Fixed size of data, fixed instance size. Everything else is fixed, just the scale.
What if you increase the size of data?
Right.
Increase size of data, then yeah, that's true. So, okay, so and finally, here's the feature work, the features of cloud clustering that needed more than those 7 weeks that I had. So I'd love to come back here again and build them, of course. So here we go. So first of all, any questions? First of all, a compromise between worker pools and data affinity. So worker pools, what was that standard architecture? Data affinity was the one with each worker has its own queue. So a compromise that retains that scalability and fault tolerance. The buddy system, as I mentioned, where each worker here's some details. So workers in different fault domains would check each other's status and take on the unfinished tasks that a failed worker has left. So, I have a buddy. If he dies, then take his task and work on it. So, secondly, improved caching using blocks. So, as I also mentioned, reusing that cache when things scale. And then fundamental improvements to the algorithm. So the stopping condition, so using centroids rather than points would help us, would eliminate that right direction. And so workers can just compute pure computation. And then also lazy computation that eliminates those synchronization barriers. So here, each iteration sort of fans out and comes back in. And then at each coming back in point, there's a synchronization barrier that wastes the worker's time. So some sort of lazy system where basically workers would asynchronously update the centroids and using partial information, and then instead of having a server wait for all of this information from one iteration and recalculate them all in one go to get the most accuracy, we could go for sort of a less accurate but faster version. And
so
also
the server is lazy. So you receive partial results, recalculate the partial new locations for the new centroids, and say those works already finished, start doing it.
Yes,
maybe
those are already
maybe they should have waited for the end, but that's.
Yeah, exactly. So instead of having workers wait for the server to give them their new tasks, they just start immediately on whatever centroids data is already there. Just keep working.
So it's not lazy; it's a speculative.
Speculative, yeah, that's true. Yeah, lazy is not really. I was sort of thinking of maybe like lazy computation of the centroids. Like we just compute whenever they're available.
Just wondering the conversion.
Yeah, that's true. This whole testing is still to be done. And then further optimizations to multi-core. So that I mentioned open up more I/O channels than there are cores. So this would just make things more efficient on even small worker sizes. All right. So here's my contact info. Any questions that you might have?
So we're letting him actually leave?
I know. I tried to convince him to start later, but I don't think it's going to work. Great talk. Nice work. 7 weeks, wow.